Welcome to MAE 242, Recitation 4. We'll be going over two problems real quick in this one. This first one has to do with finding an analytic formula for the vertical and horizontal forces on each of the semicircular panels A, B in the figure within the papers B. Which force is larger and why? There's really not too much math involved in this one. This is purely, just a proof of like buoyant force stuff. So, yeah, so let's just go through it fast. The second question is a little more in depth, so I'll go over that one a little better. But yeah, so we've got this cutout area here in this left one, and then this right one has the filled in hemisphere semicircle. So we're going to analyze force on this. Obviously, if you go and do the horizontal forces on them, it's rho g, which is gamma, times height of the centroid times the projected area. So height of the centroid would just be this middle part right here, so it would be h plus d over 2 would be the height of the centroid, and then the area is obviously just a rectangular projected area. And so the horizontal forces obviously on both are going to be the same regardless. Hopefully you guys can see that no matter what, because the height of the water is the same and it's the same projected area, but one's curved concavely and the other is convex. So that's that. Hopefully that's easy enough for you. Just this horizontal force is purely a function of height. So height of the centroid. So that's not too bad. And then for the vertical force, we're looking at rho times g times the volume that the hemisphere is taking up, right? It's kind of a buoyant force looking kind of thing. So on this left one, you can see that the hemisphere is like etching out a volume from the water. So this would be like a buoyant force kind of vibe, you know? So this one would be pushing upward. This force would kind of be pushing upward in this sort of direction, right? Whereas the one on the right, it's having water inside of it. So this whole volume would be, the force would be pushing outward like that, right? So again, same force, same overall force, but just acting in a different direction because one has an absence of water and the other has water. But because we know about the laws of like force of buoyancy and stuff, it's the force generated is the volume of water that it's displacing. So the displacement in the left is equal to the actual amount of volume in the right one. So different directions, but same overall force. With buoyancy and things like that. So that's why I'm not going too deep into it. It's just another little analytical proof sort of thing, just reinforcing the concept. And always remember that forces act perpendicular to the surface you're working with, right? Always at a right angle. So even if it's a circle, you know, it's still, or you know, I guess physically it'd be like that. Always at a right angle. It's always at a right angle. Some of you guys messed that up on the exam with the force on the submerged object. It's always at a right angle. Doesn't matter how you orient, how you find out that force, but once you go and calculate it, it's always at a right angle. Cool. Cool. All right. Now question 2 actually has quite a bit of math in it, so that's an interesting one. It's cool. It's pretty in depth. Yeah, like I said, I'm gonna skip the second part of it and we'll just talk about it. It's a little more than what I think you guys would need, especially since we've already kind of taken an exam on most of this stuff. Even though I do think there will probably be a curved surface question on your exam too. There was on mine when I took this class. But anyway, like I said, if you want to read all this stuff about it, yeah, so like here's the volume, you know, d squared over 2 times pi over 2 is half of the circle times the base. It's the same volume, but one is etching out water, one has water in it, so different direction. All right, now here's this sucker. Okay, so we've got a block of solid polyethylene, density of 860 kilograms per cubic meter, with triangle cross section floating in water. This cross section is an isosceles triangle, angles 90, 45, and 45, respectively, as shown. For orientation A, obviously the orientation in the picture, find the depth of the block. Okay, so first we're just going to get some values straight up. So we draw our triangle. So we're going to call this L right here. going to call the total height H max. And then we also know it's, 10 centimeters under the page or whatever. We can call that B. Kind of wrote that small, but it's B. Usually we'll denote B as into some length into the page, like the base. So it's pretty standard. So B into the page. And then H max, if you do, if you want to do your triangles and stuff. So you'll end up finding that H max, maximum height of the triangle, is just L over 2. That comes from your, tangent theta, it'd be H max over L equals tangent theta, all that stuff. Or L over 2 is tangent theta, so yeah. Anyway, H max is L over 2. So now we've got our total, our maximum values. So now we're going to redraw it one more time. We're just going to define some arbitrary water line. And we're just going to set like right here, okay? And we're going to call this little LS value right here the submerged length, the length of the submerged section. And this H right here is the new height of the mini submerged triangle. And then it's not in the key, but I'm going to define an H star right here, which is that's the actual depth we're finding, where H star equals H max minus H, so equals depth. Okay, and then obviously we still have our big H max right here. All right, cool. So now we've got all of that figured out. So let's start with, let's find the weight of the block first, just the total weight of the block. So weight of the block is equal to density of the block times gravity times the volume of the block. So weight of the block equals rho b g times 1/2 base times height times width. So base, and the height is H max, and the width is L, right? So cool, we got all that done. Nice. So let's do a little, save that for later, we'll need that for later. Now let's also find the weight. So we're gonna find, obviously we wanna find the buoyant force that we're generating, right? So we'll also say, and I'll go over here. So I also wanna say FB, buoyant force, is equal to rho water times gravity times the volume of the submerged portion of this triangle, this thing, or in this case, this is the submerged volume. And obviously V submerged, V sub equals V block, the total volume of the block, minus V unsub, damn it, unsub, man. Cool, but yeah, everybody following so far? Everybody cool with what we're doing so far? Yeah, nothing too crazy. I would just find a bunch of weights, rho GH stuff, rho GV stuff. So we already found the volume of the unsub, well, I guess we haven't yet, but we kind of did. All right, so V sub equals volume of the block, which is, we already said, is 1/2 base times length times H max. Now we're going minus this section up here, which is the same exact vibe triangle. So it's still 1/2 base, but now it's LS times little h. So that's the volume of the unsubmerged thing. And I'll clean up some terms. Let's go. V sub equals 1/2 base L H max minus LS H. Cool. So now let's plug this into our buoyant force. So we've got FB equals rho WG times 1/2 base LH max minus LSH. Now it's tempting to like go and sub in these values right now where H max is L over 2. And oh yeah, I forgot to say LS, by the same definition as like over here. LS is just 2H, you know, obviously multiply that over, it's the same relation. It's a nice sausage triangle. Same sort of relation. Now it's tempting to like go and sub these in right now, but we're going to be solving for h here in a sec. So it's just a little easier to clean up terms. We just leave it like this so far. So let's keep plugging in. So now we found our buoyant force, right? And we've got another equation that also has some sort of like h value vibe in it with the density of the block itself, which is integral for finding all this other stuff. So we're going to equate the weight of the block and the buoyant force so we can go and solve for that h, right? So let's do this down here. We've got FB equals WB. So we've got rho WG 1/2 base L H max minus LSH equals weight of the block rho BG 1/2 B H max L. Cool, so now let's regroup some terms, simplify some stuff, right? So obviously the G's go away, the halves go away, the base goes away. Now we're left with, I'll just go right here. All right, so now we're left with rho W equals, hold on, rho W L H max minus LSH equals rho B times H max L, right? Everybody following so far? Just doing some mathematical manipulation. We're just trying to isolate that H value because that's kind of the crux of the whole situation we got going here. Okay, and I'm gonna move this over here because it's a little easier for me. All right. So let's divide the water over. We always like to have the density of the water on as the denominator or something. Water is a great reference value. What's up?
What does LS mean?
LS is the length of this little submerged section right here. Yeah, just notation. It's just a small, when we broke up this triangle, it's just the base of the smaller triangle. But it's the same relations as everything else. That's why I kind of also wrote this up.
Yeah, so wait, when you did the FB is equal to WB, how do you know for the right-hand side that you're using the total L?
For the right side? For FB equals WB?
Yeah.
Because I'm just using the weight of the total block. I'm just equating it to the weight of the entire block.
So like where does that act? That just acts at the centroid of the entire shape?
Yeah, well in this case, don't even think of it like that. Think of it as a force that's pushing up underneath the thing.
Okay.
So it would be acting at the centroid, but it's not like the force is within the thing itself. It'd be acting like at the bottom of it, pushing the whole thing up. But yeah, the line of action would be going through the centroid, which in this case is just right down the center of the thing, since it's a symmetric object. So it'd just be acting, it's gonna be legit, it would be acting at L/2 from like the left edge, or L/2 from the right edge, just right smack in the middle, acting up. But don't worry about that. We're not really finding anything having to do with the orientation of the force in this problem, so don't worry about it too much there. But physically, yeah, it would be acting at the centroid. The line of action would be through the centroid. So anyway, okay, so we're going to divide the density of water over to get LH max minus LSH equals rho B rho W times H max L. Oh, yeah. Okay. So now we're just gonna divide some more stuff over, make it look nice and pretty. So we're going to simplify this down into LH max. We're factoring out the 1 minus, factoring that out over equals LSH, right? So I added this over, subtracted that over, and then just took out the LH maps to get into this form. You can leave it in whatever simplified form you want. This is just a little prettier way of writing it, as long as you get the right answer. Once we go and plug in numbers, obviously it doesn't matter how you simplify it. The numbers will work out to be the same. So don't trip too much about the algebra of it. Just get it into the right form. So now we're going to sub in where H max equals L over 2, and LS equals 2H. All right, so get L over 2 times L times 1 minus rho B over rho W equals 2H squared. And so we get L squared. I'm going to divide this 2 over. L squared over 4 is 1 minus rho B over rho W equals H squared. Now take the square root of it. H equals square root L squared over 4 is 1 minus rho B over rho W. Cool? So that's our actual formula. And now we just go and plug in all our numbers. We know what L is. We know what the two densities are. Just plug in. And so if you plug in the numbers, this gets you 0.9354 centimeters. So that's this little height right here, okay? So now let's go back up here where we want to solve for our depth, which is our H star. So now H star equals H max, which was, H max is L over 2, so 0.5 divided by 2, 2.5. So 2.5 minus 0.9354. So H star equals depth equals 1.56-ish centimeters. Right? So that's the actual depth underneath the thing, right? So, the whole part of this, we just set some arbitrary water line and solved for the height above it of the exposed block, and then from there we could gather everything else we needed. We used the buoyant force to leverage everything, set the actual weight of the block, total weight of the block equal to the buoyant force, and solved for H by substitution and everything. Yeah.
Can you go over again, where you use rho W versus rho B?
So when we're talking about buoyant force, we always use the density of, when you're talking buoyancy, you're going to be talking about water typically. Always use the density of water, because the buoyant force, the force that is being exerted by the water onto the object floating, is always equal to the density of the water that it's floating in times the volume that is being displaced by that object.
But then but then there's the distinction in that equation right there where you have like one term as rho W and then so is rho, I thought that both the densities were due to water.
No. Rho B, the density of the block, is the property of the block itself. This is like a plastic block sitting in the water. And it has nothing to do with the water itself. That's why, when I'm taking the weight of the block, I'm multiplying by its own density. That has nothing to do with the water. The weight of this block would be the same in or out of water. But when we're talking about buoyant force, we're taking the density of the water times the volume that's being displaced. So there's that. Okay, anything else on that part? The second part we'll have to do with like the centroid and everything. I'll show you why I didn't go over it, because it would just confuse the hell out of everybody, because it's kind of gross. It has to do with like the stability point of the center of buoyancy. Like I didn't even draw it in here, but in this submerged section, there would be a center of buoyancy where the actual buoyant force would be acting. The line of action would be, and it would be like right here. Call that CV, center of buoyancy. And we'd have a YCB. It'd be like that. And I didn't go over it because it has to do with like calculating the centroid of a trapezoid, and it's just, we wouldn't make you do that. Maybe on a really mean homework if we feel like it, but I don't think we will. But any questions about this before I start scrolling down? Any last stuff? Yeah.
Yeah, and then how did you know, can you just go over the L over 2 and 2H thing again?
Okay. So let's redraw this triangle one more time. So let's just take a snapshot of this little half. Okay. So this is our theta right here. This is our 45 degrees. We want to find this H right here. right? This is our H max. And this by definition is L over 2, okay? So we know, SOHCAHTOA rules from high school. Tangent is opposite over hypotenuse. So opposite H max over L over 2 equals tangent theta, which is 45. And tangent of 45 is just 1, because it's, what is it, root 2 over 2 over root 2 over 2, unit circle stuff, so. Equals 1, multiply that over. Equals L over 2. And that's the same thing for our little triangle we drew. It's the same as that triangle, I just chopped it off at the top. So, if you also want to say like L equals 2 H max, that's where I got this LS equals 2 with the little h. Same relations, just 90% of engineering is drawing triangles, making triangles work. I learned that in dynamics. I just started drawing a bunch of triangles and stuff started working for me. So, just basic geometry. That's where you really get tossed up if you just forget your basic rules. You'll make all sorts of little numerical errors, or you'll have the concepts down, like you know how to do buoyancy stuff. But in this case, if you messed up a triangle rule, then kind of the whole problem's done from that point. Okay. Anything else for that one? Before we move on quick.
I just wanted to ask if the shape of the object matters at all for buoyancy course.
The actual shape, no, it's just the volume. It's just the volume. It can be whatever little shape, crazy shape you want, where you have to integrate over some weird parameters. Doesn't matter the shape, just the volume is all that matters. It's the same thing like, what was that last week, where we had was that the one where it had the ball that was tethered underneath the water? Like that shape of that ball didn't matter. It was just the volume. We usually just use nice objects because they're easily calculated volume. What if you give you, some crazy looking shape like this, and you say, hey, this thing is like 5 cubic meters. It doesn't matter if that 5 cubic meters is nicely shaped or not. It's just the volume that matters. Yeah, that's a good question though. All right, here we go. Anybody take a picture of this? Like I said, this will all be posted tonight, but really cool. And of course, if not, email me. People on YouTube. Okay. Yeah, the whole second part of this is all about like the stability of it and calculating that center of buoyancy. And I just don't think you guys would need to do that, but it's if you really want to get good at this stuff, this would be a great exercise to do on your own. If you've got 20 minutes of free time, go and prove this to yourself mathematically. But you won't break my heart if you don't. I think so. Yeah, so part B now. Yeah, so here's all the solution to it and everything. I went a little more in depth on the actual algebra, but yeah, here's plugging in the numbers. It's all the same stuff. Okay. So yeah, we want to inspect the stability of it. We want to calculate the center of buoyancy, would be at the centroid of the submerged area, like I was saying. And the centroid distance from the bottom is this whole equation, which you can go prove mathematically. It's just pretty gross, and I don't think you guys really need it. But go plug in all the numbers for it. Yeah, again, the center of buoyancy is negative H max.
That formula we can find under our centroid too.
Yeah, I think you can prove it. Yeah, you can prove it to yourself, but it's the centroid of the trapezoid. And if I really wanted to do it, I would probably do it where this is how I would probably do it. If I was on an exam and I really need to find that centroid, this is how I would do it. I would take my trapezoid and I'd break it up into 2 triangles and a rectangle. And I'd find like C1, C2, and C3, and then use like parallel axis theorem and all that stuff. Or I guess it would be like, it's like y bar plus y bar 1 plus y bar 2, or y bar 1a1 plus y bar 2. You know what I'm talking about. You guys take mechanics class.
So we use the trapezoid centroid because we're talking about the centroid.
Yes.
We don't use the triangle.
Yeah, because we're talking about the centroid of the submerged object. And the submerged object is like a trapezoid. So, like I said, you can prove that to yourself mathematically if you do like, that sum of, y over ya, whatever it is. I'd have to go look, but You can totally do it yourself mathematically, but we give you that sheet of centroids, just do that. So that's what you use, and that would get the centroid distance from the bottom, and then just another basic mathematical manipulation. So that's where it'd be center of gravity, center of buoyancy, negative. So yeah, there's that. Yeah, if you want to go do this mathematical exercise yourself, be my guest. If you have a question about it, email me. But other than that, should be good. Any questions on this whole problem? Questions, comments, concerns, anything like that? Cool. Like I said, pretty short one. First one is purely analytical, a lot of proof stuff, and the second one just has a little more algebra than usual, a little more in depth than what we'd usually ask. But anyway, all right, cool.